Good morning, everybody. Thank you for joining us today on another Webinar Wednesday. My name is Chris. I am the Regional Marketing Coordinator for Rothoblaas here in North America, United States and Canada. Today, we've got a guest presentation on the reuse of screws for lifting with Benjamin Herzog. As always, if you have any questions, please feel free to access the Q&A section on a computer. It will be on the top bar where you can click in and you can type your questions throughout the presentation. And if you're on a phone, you should see in the bottom right-hand corner 3 dots. That'll open up a menu and give you that option to enter into that area. We will answer questions towards the end of the presentation, so feel free to keep them coming. But without further ado, I'm going to pass it on over to Ben.
Thank you, Chris. Good morning, good afternoon, good evening, depending on where you are. Thank you for joining us today as part of this webinar, and thank you to Rothoblaas for giving me the opportunity to present. Today, we are going to be talking about reusing screws with RAPTOR plates for lifting CLT panels. But before we jump into that, I want to just spend a couple minutes explaining who I am, the center that I work at. Again, my name is Ben Herzog. I'm a wood technologist at the Advanced Structures and Composite Center. We are located on the campus of the University of Maine. The Composite Center is a world-leading interdisciplinary center for research, education, and economic development, encompassing material sciences, advanced manufacturing, and engineering of composites and structures. We've been around since about 1996 on campus at UMaine. We've grown from since that time, we've grown from 4 to 400 staff members. We've financially sponsored more than 2,600 students, received over 300 patents, welcomed over 30,000 visitors, created 15 spin-off companies, and been honored with more than 40 national and international awards for excellence. Our strategic plan, we're calling ASCC 30, focuses on expanding the frontiers of composite materials and manufacturing technologies to engineer solutions in infrastructure, energy generation, national security, while preparing future leaders to solve society's emerging challenges. If you don't know where Maine is, there's a red star on the map. We're in the northeast corner of the United States. But as you can see, our partners, collaborators, and clients are global. Our clientele represents every continent except for Antarctica. And I also want to note that we are an ISO 17025 accredited laboratory with most of the wood standards within our scope of accreditation. Obviously, I'm a wood nerd, and we're going to be talking about a lot of mass timber application here. But if you have any interest in our other research areas, please visit our website. The address is on the screen now. But let's get into the topic at hand. I am presenting the results of a initial test program initiated by Rothoblaas. Rothoblaas was interested in investigating the potential of reusing screws with the RAPTOR plate lifting hooks. If we're unfamiliar with the application of these hooks, you can see in the picture we're using these hooks to lift CLT panels from a truck or bed or some sort of or the ground into the project being constructed. It's interesting, or it's imperative to note rather, that the testing done at the University of Maine should be considered look-see testing. Rothoblaas was looking for an abbreviated test program to really suss out the potential of using screws. The testing stemming from the Composite Center that we did here at Maine justified a more robust testing campaign that Rothoblaas initiated at a European lab. And then we'll talk about this at the end. Together, the test results from Maine and Europe helped form Rothoblaas's current recommendations on screw reuse. As part of this testing, however, we performed monotonic testing of both new and reused screws. The screws specifically were HBS plate screws, and we subjected the system, the screws and the RAPTOR plate in tension, shear, and a combination of the two. Real quickly, the materials that were used as part of this test program, including the RAPTOR plates themselves, per Rothoblaas's recommendations, these plates can be used with 2, 4, or 6 screws, which must be installed symmetrically. These RAPTOR plates have been certified for weights exceeding 3 tons. Again, we were using the HBS plate screws, 10 millimeter in diameter. We used 2 different lengths, an 80 mil and a 180 millimeter length. We also did some spot tests using the new HBS PL screws. Those are shown on the right of the photo. HBSP is on the left. You'll note that the HBSPL screw has a revised geometry near the screw head, and we can talk about the potential effects of that new geometry in just a few minutes. The system, meaning the plate, the lifting plate and the screws, were used with CLT specimens that were procured from Europe and the US. European CLT was spruce dominant, manufactured with spruce and fir species, published specific gravity of 0.42, but we also did some spot tests using southern pine species CLT with a published specific gravity of 0.55. The CLT specimens were sized in such a way that the effective penetration length of the screw was 70% or greater of the member depth. This was by design in order to realize the full capacity of the lifting system as part of these tests. Also, as standard, all wood materials were conditioned, standard conditions, 20C, 65% RH, until reaching equilibrium prior to testing. In general, these conditions result in an EMC of 12% for solid wood. Let's spend a second talking about loading and how we loaded these specimens. But first, I want to maybe define some terms that we're going to be talking about throughout the rest of the presentation. I think we all know what the working load limit means, WLL. This is the maximum allowable load of the system. Again, system being defined as the screws and the RAPTOR plates in tandem, and of course by loading direction, tension, shear, or a combination of the two. We followed ISO 6891 as part of the loading. So again, actually going back to the definitions real quick, forgive me, but we know what the working load limit is. Characteristic value, F sub K, that's defined as 4 times the working load limit. And estimated maximum load, F sub estimate, is defined as 1.3 to 1.5 times the characteristic value, meaning that the estimated failure load is 5.2 to 6 times the working load limit. When we were testing the new screws, we used an estimated failure load, which was provided by Rothoblaas for this testing. And again, we loaded per ISO 6891. Assemblies were loaded to 40% of the estimated failure load over 2 minutes, maintained for 30 seconds. The load was then reduced to 10% of the estimated failure load and maintained for 30 seconds. The assembly was then reloaded to failure. Reused screws were done slightly differently. The way we looked at this is how we're defining the reused screws. A set of screws were installed into a CLT specimen and loaded. After the loading regime, the screws were withdrawn from the sample, as was the RAPTOR plate, and both the plate and the screws were then attached to a new piece of CLT. Efforts were done to make sure that the screws were placed in the same location within the RAPTOR plate every time. We did this a total of 4 times. And then on the 5th time, we loaded to failure. So CLT pieces 1 through 4 were loaded up to a cycle load, F sub cycle, as part of this slide. The cycle load is defined as 50% of the estimated failure load. This equates to 2.6 times to 3 times the working load limit. And then on the 5th cycle of the reused tests, we reverted back to the estimated failure load as part of the loading regime. So I guess the point that the real point that I want to make here is that these screws were pretty stressed. We took these up to some significant loads, well beyond the working load limit, even as part of the reused screw cycling. Again, we loaded in tension, shear, and a combination of the two. Here is a diagram, or a photographic image of the setup for tension. Screws were installed at a 90-degree insertion angle to the CLT face. We implemented procedures in the lab to make sure that that angle was adhered to and screws were not overdriven, over torqued, etc. The CLT specimen was restrained to prohibit movement, both vertically and horizontal movement. And as part of the tension tests, a vertical load parallel to the screw orientation was applied to the RAPTOR plate itself. Maximum load and failure modes were reported for each specimen. I noted this at the beginning of the presentation, but these are check tests. This is a look-see test, very initial. So the sample sizes that you see on the screen are very, very small. Again, the objective here was to see, was the suss out potential. The focus really was on looking at the first 2 rows, which are shaded in green on your screen. T1 and T2. T1 was the new screws. T2 was reused screws. 4 screws per RAPTOR plate. This was done using the spruce CLT, and these were the HPSP screws. The top row is for the 80 mil screws, and the second row is for the 180 mil screws. 3 specimens were tested for both the new and the reused screws. And then on my screen, it's a pink color. Rows 3, 4, 5, and 6. Consider these to be just spot tests. Row 3 and 4, we're looking at 4 screws attached to the RAPTOR plate, looking at the Southern Pine CLT. So replicates of rows 1 and 2, just with the Southern Pine higher density CLT. T9, T10, we went back to the spruce CLT, but only loaded with 2 screws. T11 and T12, spruce CLT, but maxed out the Raptor plate by using 6 screws per specimen. Results are shown here, and let's see if I can do this a little bit more efficiently. In this column here is our estimated failure load, again defined by Rothoblaas, and provided to us to use as part of the loading regimen. And here we can see a combination. So here's our new screw, average new screw failure load, average reuse screw failure load. You can see that these results are very, very similar. That trend holds true when we are looking at the longer 180 mil screws. And that trend does repeat even with these spot tests on the Southern Pine CLT, 2 screws in the Raptor plate, spruce CLT, 6 screws in the Raptor plate, spruce CLT. So not much of a difference between new and reused screws. And in my mind, that's what we're really looking for. I'm not really getting hung up on comparing the test results to the estimated failure loads. What I'm generally interested in is reuse versus new. The 80 mil screws failed in withdrawal. This was regardless of wood species, regardless whether we were testing new screws or reused screws. With the longer screws, we didn't see withdrawal. Well, I'm sorry, we did see some withdrawal, but we also saw a lot of plate deformation, as you can see from that video there, across the board, plate bending, and then we saw some wood failure. With screw withdrawal, as you can see from this image here, or we saw some screw head rupture, as you can see here. The video was showing a combination of the two. Plate bending, followed by some screw head rupture, and then some screw withdrawal. The difference in failure mode as a function of new versus reused screws was not readily apparent. In other words, we saw this combination of failure modes regardless of whether the screws were quote unquote new or reused. The shear testing was done in a similar fashion. Screws were installed 90 degrees to the CLT face. Wood member was restrained from movement, and a vertical load perpendicular to the screw orientation was applied to the Raptor plate. We had to get a little bit creative on how to maintain that perfect 90-degree loading direction, but I think we did a pretty good job with that. Again, failure load and failure modes were recorded and reported for every specimen. This matrix should look very similar. It's basically a replicate of the testing matrix we did for tension. Again, the focus was on the spruce CLT with 4 screws using the HBSP screw lengths. The results showed some decreases in ultimate load compared to the new versus reused. For the 4 screws, spruce CLT, 80 mil screws, we saw a slight decrease of new versus reused screw. And that trend did hold true for all other tested cells. Slight decrease on the 180 from 70.6 kilonewtons to 60.2. And we saw that with the Southern Pine CLT as well as spruce CLT with 2 or 6 screws implemented with the Raptor plate. When we were looking at the 80 mil length screws, we saw withdrawal of the 2 lower screws, which allowed the plate to pivot upwards, causing the upper screws to deform and then withdraw. We did see some CLT damage, of course, during the loading. In fact, we did have two specimens where we saw some CLT failure. And basically, I think you'd consider this almost cleavage of the CLT in the transverse direction. These were done, we saw, it's probably coincidence, but these were both new screws that we saw this failure mode in. When we're looking at the 180 length screws failed in screwhead rupture. And I showed this video in particular because these screw heads, when they failed, they became little bullets, and one of these screw heads actually knocked over our camera during the testing, which I thought was funny. I want to note that these videos that I'm presenting are 5 seconds, 5 to 10 seconds of a 10-minute test. And as we go through, you'll be able to note that we trace these RAPTOR plates on the CLT specimen prior to loading, so we could also look to see how far these plates moved on the CLT as part of the loading. And if you've done any testing of wood before, you know that 99% of the 10-minute test is pretty boring. It's only the 5% that's exciting at the end. We knew when these were going to fail. You can hear the wood splitting, you can hear the metal weakening. And so, although we had one of these screw heads hit our camera, we knew and were able to take safety precautions well in advance. Combined tension shear. Well, I think these diagrams shown on the screen really kind of show what we did as part of this. We developed a test fixture to situate the CLT such that we were maintaining a target angle of 45 degrees from the axis perpendicular to the surface plane of the CLT. Again, steps were taken to eliminate any movement of the CLT as part of the testing. The vertical load was applied to the RAPTOR plate, resulting in both tensile and shear forces imparted on the system. Again, this test matrix should look familiar to you. It's a replicate of what we did with the tension and the shear tests. However, I do want to note this last row. This is a new row here where we were looking at the HBS PL screws. This is the new screw geometry that I showed in an earlier slide. We just did a couple specimens each looking at the new and the reused screws. And spoiler alert, this did change the failure mode significantly. Kind of a mixed bag in terms of the results here. In some cases, there was essentially no difference in average ultimate load between the new screws and reused screws. I would suggest that the highlighted rows show no significant difference between the two. In other cases, we did see some greater differences between new and reused screws, as you can see from the table. But again, my disclaimer, very, very small sample sizes make conclusions difficult. But let's look at some videos. The 80 mil screws were very, very similar to the shear tests. We saw the downhill screws withdraw, generally most of the time causing splitting of the lumber, also allowing the plate to pivot up, resulting in the uphill screws deforming and generally withdrawing from the CLT specimen in itself. And, from your screen, you can see where the plate was originally positioned and how much it did move as part of the loading regime. With the 180 millimeter HBSP screws, primary failure mode was screwhead rupture. This was combined with screw withdrawal in some cases. You can see compression at the top of the CLT specimen due to the pivoting of the plate when under load. And let's get to the HBSPL screws, 180 mil lengths. You can see that this plate did travel, quote unquote, uphill quite a way, but instead of any screw head rupture, all 4 screws withdrew from the specimen itself. So what should we take from this? Well, not to sound like a broken record, but the sample size was incredibly small, making it difficult, if not impossible, to make any conclusions. The objective was not necessarily to confirm design values or recommendations as part of this testing here at Maine, but to better understand the mechanics of the system. Again, this led to a much more robust testing campaign conducted in Europe. And the combination of the 2 testing programs were done to help identify factors that may influence differences in ultimate load seen in the field between new and reused screws. These factors may include incorrect installation, such as improper insertion angle or over torque of the screw, or system overloading, damage to threads as part of reuse, etc. Also, again, remember that our estimated failure load was up to 6 times the working load limit, and the cycled load that we use for the reuse screws was 2.5 to 3 times the working load limit. Again, this was by design. We're looking to see what happens to the system under extreme conditions. The other thing I want to note is that we did take a specific gravity measurements of representative CLT specimens after the testing. And both the spruce and the southern pine CLT were a little light in terms of density. Spruce averaged about 0.4 specific gravity. The southern pine had an average specific gravity of about 0.5, as opposed to the 0.55 and the 0.42 for spruce, respectively. So I think we can consider the test results as part of this program on the conservative side. If the CLT, had a density more in line with those that we use for design, we'd expect loads to be even higher than what we saw. So just a quick snapshot of the results itself. When we looking back again at the tension tests, reused screws on average had a 96 to 105% capacity of new screws. No difference, I think we could say. When we are looking at the shear tests, the reused screws range from about 80 to 90% capacity of that of new screws. So again, let's not forget about the fact that our cycled load as part of the reused screws was extremely high, well above beyond the working load limit of the system. And also, let's talk just a little bit about the ductility of these 2 different systems. Shear has a higher ultimate stress to yield ratio, resulting in greater ductility, while the opposite is true with the tension tests. Those had very, very low ductility. The combined tension shear tests, when we looked at the 80 millimeter HBSP screws, Does not look like repeated loading affected the screw capacity. When we looked at the spruce CLT, unclear if that trend holds true for the southern pine CLT. Believe it or not, the new screw results were highly variable. We might think that the reused screws results would be more variable, but that we did not see that as part of the limited testing we did at Maine. We'd have to assume that had to do with the variability of the CLT used for testing here. The HBSP 180 millimeter length screws, kind of a mixed bag. If looking at the ratio of reuse to new screw capacity, it ranged from about 75% to 100%, give or take. But again, most of these were a sample size of one. So, and then we talked about it a little bit before, the new screw geometry of the PL screws. That revised profile reduced the screwhead rupture failure mode and moved that into a screw withdrawal failure mode. And based on a sample size of 2, the reused screws had a 94% capacity of the new screws. So again, at the risk of repeating myself, these were initial look-see tests. More robust testing has been done. Again, the ultimate goal was to understand the mechanics of the system. The testing was designed to demonstrate the screw's ability to maintain its performance under simulated exceptional stresses and potential risk conditions associated with reuse. The full suite of tests done at the European lab generally confirmed the behaviors and the results generated at the Composite Center at Maine. And further analysis from these data confirmed that at the working load limit levels, all screws, whether new or reused, were well under the yield point, i.e. within the elastic range of the screw. And again, these data were used by Rothoblaas to develop their current recommendations. That's the testing in a nutshell done at Maine. I'm happy to field any questions from the group.
I'm looking here in the Q&A section, and in the current moment, I don't see any written questions, but I'll also open the floor to our technical team that's here on the call. Looks like we're a little bit quiet today. That's
And
okay.
that is fine with me, Chris. But I do like to talk, and so I do want to thank Rothoblaas for their support. I can't say enough good things about Rothoblaas, both as a client but also as a company. I think that this started with my understanding, this came from a question from users, and it's a great question, right? And so Rothoblaas took the time to really fully vet this question and issue out, and we look forward to working more with Rothoblaas in the future.
Awesome. Thank you. Yeah, as always, I always kind of close out with this. If anybody ever has any questions, whether it's immediately after this presentation, an hour, a day, a week, a month, or even a year, you can get with us at eng.na at rothoblaas.com. And for this webinar in particular, if you do have any questions directly for Ben, we can make sure to pass that along to him and make sure to get you connected. So we look forward to seeing you all in the future at events, in person and of course digitally on another webinar. We do have a few more webinars the rest of this month and throughout March before we announce our quarter 2 webinars. So enjoy the rest of your day, stay warm, and thanks again for attending.
Thanks, everyone.